In this video, I'm going to look at gravitational potential energy, kinetic energy, and elastic potential energy. We will see the equations and ultimately how we deal with questions that involve transfers between these different types of energy. These questions can be worth up to a valuable 6 marks. Throughout this video, it's worth remembering that the change in energy of an object is the same thing as the work done on the object. Change in energy is just equal to work done. So if I talk about work being done, I'm talking about the amount of energy changing. Let's kick off with gravitational potential energy. This book has gravitational potential energy. It's called potential energy because the energy stored in the object's position, the book's position, it has the potential to be released as a more useful or observable form of energy. If I were to knock the book off the shelf, then its gravitational potential energy would be converted into kinetic energy. Sorry, Einstein. More about that later. For now, let's look at gravitational potential energy stored. The amount of energy stored depends upon 3 things. Firstly, the mass of the object. The more massive it is, the more energy it has stored in it. Secondly, the height of the object. The higher the object, the more energy it has stored in it. The third thing to consider is the strength of the gravitational field. On Earth, the gravitational field is around 10 newtons per kilogram, sometimes written as 10 meters per second squared. These units are equivalent and interchangeable. While some examples and questions use a gravitational field strength of 10, you'll probably be asked to use the more precise value of 9.8 newtons per kilogram. Of course, this value of G will be different if you travel to another planet or elsewhere in the universe. On the Moon, for example, it's around 6 times less, at around 1.6 newtons per kilogram. Combining these factors that affect the gravitational potential energy, we get the change in gravitational potential energy equals mass times the gravitational field strength times the change in height, or delta E little p for potential equals mg delta h. You won't always see the delta symbol used, but I prefer to include it. It reminds me that we're talking about the change in energy and not the total energy. Imagine my book falling to the floor. When it's on the floor, it doesn't have 0 gravitational potential energy. If I dug a hole underneath it, it'd fall into that hole and have even less energy. And you can't have negative energy, so it's definitely not got 0 when it's sat on the floor. Here's a quick example. I lift a box from 0.5 meters above the ground to 1 meter above the ground. What is the change in gravitational potential energy? If the box has a mass of 1.5 kilograms, delta E equals mg delta h, which equals 1.5 times 9.8 times 1 minus 0.5 for the change in height. And that equals 7.35 joules. Kinetic energy is movement energy. Once again, the more mass a moving object has, the higher its kinetic energy. The other factor affecting kinetic energy is the speed of the object. Speed has a big effect, and if you double the speed, then the kinetic energy goes up by 4 times. This is one reason why increasing the speed of a car a little makes it a lot more dangerous than most people realise. The equation for kinetic energy is kinetic energy equals half times mass times the speed squared. In simple form, it looks like this. E little k for kinetic equals half mv squared. Let's look at an example. What is the kinetic energy of a 1500 kilogram car travelling at 13 meters per second, which is approximately 30 miles an hour? EK equals half mv squared, which equals half times 1500 times 13 squared, which equals 126,750 joules. What happens if we increase the speed to 16 meters per second? That's approximately 35 miles per hour. EK equals half mv squared, which equals a half times 1500 times 16 squared, which equals 192,000 joules. You can hopefully see this is a significant increase in energy for just a small increase in speed, which is why it's best to drive slowly in built-up areas. This can be a tricky equation to rearrange, but I'm not going to go into lots of examples here. I'll produce another video on how to use and rearrange formulae, so please do subscribe and come back to view that. Finally, we have elastic potential energy. This is the energy stored in a stretched object, such as a bow or a catapult. The energy stored depends on how far something is stretched, what we call its extension. It also depends on how stretchy the object is. We describe the stiffness of a spring or stretched object using the spring constant. The spring constant is measured in newtons per meter. Here is the equation. Elastic potential energy equals half times the spring constant times the extension squared. E, little e for elastic, equals half KE squared. For example, a spring with a spring constant of 12 newtons per metre is stretched by 10 centimetres. How much energy is stored in the stretched spring? E equals a half KE squared, which equals half times 12 times 0.1 squared, which equals 0.06 joules. Notice that we need to convert the 10 centimetres into metres. 10 centimetres equals 0.1 metres. So that is our three equations. Now let's have a look at some problems where we need to combine them. Before I do that, I should point out to you that I have some free downloadable questions to go along with this video, as well as worked answers. They're available from my website and I've included a link in the description below. Please also take a moment to like, subscribe and even comment. Without that support, I'm not able to continue producing videos and resources. Now it's time to combine these forms of energy and their equations. To start with, let's have a look at falling objects. If I drop two objects out of a window, one with a large mass and one with a small mass, which one hits the ground first? Well, let's put some numbers into this problem. The height of the window is 5 metres. The mass of the first object is 2 kilograms, and the mass of the second object is 6 kilograms. The change in potential energy of the two objects is therefore mg delta H, which is 5 times 9.8 times 2, which equals 98 joules. And delta EP equals mg delta H, which is 5 times 9.8 times 6, which equals 294 joules. As the two objects fall, the gravitational potential energy decreases and the kinetic energy increases. When the objects hit the ground, they have lost this change in gravitational potential energy, and it's all turned into kinetic energy. We can use this to find out how fast the objects are going as they hit the ground. Let's start with the 2 kilogram mass. So the kinetic energy is half mv squared. So as we said, that kinetic energy becomes 98 joules, which is half times 2 times v squared. We can simplify this, so 98 equals v squared. And so v equals the square root of 98, which is 9.9 meters per second. Now let's do the same for the 6 kilogram mass. The kinetic energy is half mv squared. The kinetic energy is got from the gravitational potential energy, so that's 294, and that equals a half times 6 times v squared. Simplifying this equation, we get 294 equals 3 times v squared. So 294 divided by 3 equals v squared, and thus 98 equals v squared. You may have spotted something already. For the 6 kilogram mass, v equals root 98, which equals 9.9 meters per second. So both objects hit the ground with the same speed. Famously, it was Galileo Galilei that pointed out that all objects fall with the same acceleration and will hit the ground together, provided that there's no air resistance. I can show you this by just looking at the equation. We said that the gravitational potential energy turns to kinetic energy, which means that change in gravitational potential energy equals change in kinetic energy. So mgh equals half mv squared. The masses cancel, so mass has no influence on the speed of falling objects. Finally, let's look at stretching objects. When we stretch a spring, we store elastic potential energy in the spring. But when it's released as kinetic energy. Imagine a bungee jumper. They start off with gravitational potential energy, which then turns into kinetic energy as they fall, which then becomes elastic potential energy as the bungee stretches. Calculations about a bungee jumper are probably a little too complicated for GCSE, and so let's look at a simpler example. A catapult with a spring constant of 25 newtons per metre is stretched by 15 centimetres. At what speed can it launch a 250 gram mass? We begin by calculating the elastic potential stored in the stretched catapult. So E equals half KE squared, which equals half times 25 times 0.15 squared, which equals 2,812.5 joules. This energy is then converted into the kinetic energy of the launched object. So EK is half mv squared, which is equal to 2,812.5, which equals a half times 0.250 times v squared. Remember, we've converted the 250 grams into 0.25 kilograms. 2,812.5 equals 0.125 times v squared. So 2,812.5 divided by 0.125 equals v squared, and 22,500 equals v squared. So we square root that and get a velocity of 150 meters per second. That is seriously fast. Faster than a plane is catapulted from an aircraft carrier. This is a very challenging example, so if you've understood it, well done. If not, do watch it again and try the free practice questions. When you're ready, here's something else to watch.